Hello and welcome to the third part of this video series, where in this video we'll be deriving the Rockford-Rice equation for an n-component flash calculation for a given temperature and pressure, which for later we'll be using that derivation to utilize and find the different compositions and flow rates for the outgoing vapor and liquid phases. So to start off, what is a flash calculation? Well, in a flash calculation we have a flash drum, or we have some sort of container, and we have a feed going into this flash drum, right? And this feed is calculated in moles per second, obviously, for the amount of quantity of moles that the n components within the feed has. And as this feed goes into this flash drum, it separates into two different things. It separates into the vapor phase, and it separates onto the liquid phase. And both of these phases, both of these sides, have a little tube connected to them that helps both the vapor phase and the liquid phase go out and continue on into a longer process in a manufacturing plant or something. But we don't care at the moment. We're only focusing on the flash drum aspect of it. So we have this flash drum, and we see that it's at set temperature and set pressure, right? And we have this quantity going in of F moles, and we actually know that the mole ratio for this is 0.4. And later on, we'll be using benzene, or we'll be using benzene and toluene, and this meaning that benzene has, let's say for 10 moles per second, benzene has a 4 moles per second, and toluene goes in at 6 moles per second. And yeah, so this is a flash calculation, or a flash drum, and how it works. And so now we'll be deriving, we'll be utilizing different equations that we know to find some final equations, find a final equation that we can derive and utilize in our code. So I'm going to write my equations here. Before we start, there's a few couple of picky equations that we need to remember and recall later on, so I'm going to write them over here. The first one may seem kind of obvious, but we still need to know and remember is Raoult's law, right? We just went over this earlier in this video. So the amount of moles in the liquid phase multiplied by the purely saturated component in the vapor phase is equal to the mole concentration in the vapor phase multiplied by the pressure. We know that this Y1P is also known as the partial pressure, right? Aside from this, we need to know a mass balance equation that we'll be using, and that equation is that the feed F is simply going to have to equal to V plus L, right? Whatever is going in has to come out, yeah? If we have 10 moles going in, we need 10 moles coming out. Either it be 5 and 5 or 2 and 8, however it may be, we need the same amount on both sides. We can't have something stuck in here. The same amount of moles will be carrying on into the process, right? And from here, we can also create another mass balance equation, right? We can write that the multiplies by Z1, right? We know that if we multiply the amount of moles that the mole concentration multiplied by the amount of moles of benzene multiplied by the feed, it's going to be equal to the Y1, which is the amount of mole concentration in the vapor phase multiplied by V, plus X1 multiplied by L, right? Just simply multiplying and demonstrating that how the mole ratios and concentration, or mole ratios, connect throughout. And before we get started, continue writing our equation, I want to create a new variable from this Raoult's law that we have over here. And I'm going to create a new variable. Let's call it K, or call it Ki. And just simply going to be the ratio between these two. We're going to have Y1, which is the mole fraction in the liquid, or in the vapor phase, divided by the mole fraction in the liquid phase. Or can equal this also as the purely saturated component in the vapor phase divided by the total pressure, right? Right. And from here we can also rewrite this as xi ki is equal to yi or something like that. So I'm just gonna simplify this a little bit down, write this as yi, or the component in the or the mole fraction in the vapor phase is equal to Ki multiplied by the mole fraction in the liquid phase. Then from here, we can starting with our equations. And the first thing we want to write down is from a mass balance, another mass balance equation, which is represents the summation. And sorry, I lost my mouse. Okay. And what it is the summation of the mole fraction in the vapor phase subtracted by the summation of the mole fraction in the liquid phase is simply going to be equal to 0, right? It's fairly straightforward. It's just saying 1 minus 1 is equal to 0, right? Nothing too crazy saying here. And then from here we can also just simply rewrite this as just the total summation of the mole fractions in the vapor phase minus those in the liquid phase. It's going to be equal to 0, right? However, we don't know either y1 or x1. We want to rewrite this with some of these variables that we have here, right? So the first thing I'm going to do is replace yi with k1 x1. So if we do that, we'd have k1 x1 minus x1. So we can also rewrite this as simply the multiplication of the mole fraction in the vapor phase, or in the liquid phase, multiplied by ki minus 1, right? Because it would be ki x1 minus x1, right? Just write this in the parentheses so we can easier write it down. This is equal to 0. Now we got the first one, but now we want to get x1 out, right? We want to figure out how we can correlate that back here without it being an unknown. So we're going to go look back at this mass balance equation that I wrote over here. And what we're going to do is we're going to work on it, right? So the first thing we're going to do is multiply or reconnect this yi that I solved over here into this equation, right? So starting with that, we then have z1 multiplied by f, so the fraction of benzene multiplied by the feed is now going to be equal to k1 x1 v plus x1 L, right? And again, we see that there are some common factors here, right? We know that there's an x1, so I'm going to go ahead and do that, bring that out, so that this now becomes the mole fraction in benzene multiplied by the feed is simply going to be equal to x1, the mole fraction in the liquid phase, multiplied by L plus I have K1V, right? This is what we'd have, right? So then we can go ahead and divide this out, right? We'll divide the left side by L plus K1 over V, right? So that we finally get x1 is equal to z1 multiplied by f all over L plus K1 V, right? Now what we can do from here is that we can replace this L that we have here with this mass balance equation that we had earlier, right? We can rewrite this to be as L is equal to F minus V, right? The what is going out in the liquid phase must be equal to the feed minus the vapor phase, right? Common sense. So go ahead and rewrite that as V1 multiplied by F, or the fraction of benzene multiplied by the feed. We have, we were writing for L, sorry. So then now we have F minus V, and then we have F minus V plus Ki times V, so I'm just going to do F plus V, right? And just simply multiply it by Ki minus 1. Right? It's the same thing, just trying to simplify this out. Then from here, we have an F, so we can go ahead, the feed, and we can go ahead and take that out, divide it both sides, or divide it total. So you have Z1 is equal to 1 plus what's going on in the vapor phase divided by the feed multiplied by K1 minus 1. Alright. Then from here, we can simply go ahead and bring back this equation that we were at back here. Right? This is where this comes in now. We can rewrite this and simplify it into here as we had x1 is equal to z1 over this. Right? So now that we can rewrite this as z1 multiplied by k1 minus 1 all over 1 plus v over f multiplied by the same thing in the numerator, ki minus 1, right? Then of course this is going to be the summation of these values, and if you read the question, it asks for an n component flash calculation, so we're acting as if there are n amount components. So this summation is going to be from I equals 1 all the way to n, right? For no matter how many components, we can utilize this equation for a flash drum calculation, right? And so now we can go ahead and put this into Python and go from there. So check out the next video. Thank you.